We're going to be going over cleaning residual 1/f noise in near-spec MOS products with NSClean, which is a new algorithm that has been implemented in the pipeline. So just to go a little bit again, just give you a brief idea about what's in this notebook. You'll have like introduction, your imports, you're downloading the data, and then we'll go through running the pipeline on this stage 2 on this data without NSClean applied to give this sort of baseline. And reference point, we'll then go ahead and run NSClean on the data, but using the default pipeline mask. I'll explain a little bit more about what the mask actually is in a second. But there are some few ways that you can do the mask. So we're going to try to edit some of the parameters and provide an alternate mask to compare. And then we're going to also show just a quick example of how you can modify a mask by hand and provide it to the pipeline. So just to give a little bit of background introduction on, the problem at hand and what NSClean is kind of doing. So NearSpec has a few features and characteristics that we should all be aware of when we're observing or interpreting the data. And one of these is these negative or surplus flux that can be seen in your extracted 1D spectra. It's typically irregular wavelength dependent undulation, and the cause of this is correlated read noise, or also known as 1/f noise, and it comes from the low-level detector thermal instabilities. And so if you're looking at a rate image, which we'll see in a few cells down, these show up as these vertical banding in your 2D rate images. And if you look at NRS2 compared to NRS1, you'll notice that the 1/f noise is a lot more prominent in the NRS2 detectors. And we do note that the IRS square readout mode reduces the effect, but it's not completely eliminated. And so to address this, the pipeline has integrated this package called NSClean, developed by Bernard Rauscher, and it has been implemented in the Spec2 pipeline, and it's under this step now called NSClean step. And so essentially, the algorithm is using the dark areas on the detector to fit a background model to the data in Fourier space. But it does require you to have like this input mask to identify what areas on the detector are dark and which areas on the detector are illuminated. And of course, the more complete your mask is, the better your background fit will be. And so I've kind of already outlined above what we're going to be looking at. So let's just go right in. Here, you're just going to do, again, general imports. We're also, I should have noted this in the other one too, but there's some functions I'm pulling from another .py file to do some of the plotting, so it doesn't clutter up this notebook. And again, we're using the latest version of the pipeline here. So a little bit about what data we're actually using in this. So the data for this demo is a MOS observation from the SEERS program. It's coming from ERS program 1345, observation 61 specifically. And it's using a high resolution grading G395H. And this has multiple exposures, but we only are pulling one of the dithered exposures to demonstrate the results of NSClean. So here we're just downloading the data. And of course, we also need to download the MSA metadata file so that the pipeline can run. Okay, so in this very first section, it's just running the default, Spec2 pipeline on this data without NSClean. So we're just going to make sure to skip NSClean. Another thing I'll just note here is that in this data, I'm only going to extract one slit from each detector. And you can kind of define that in the extract 2D parameters with this slit name parameter. So this will just give us a baseline. We'll see some of the original results in the next plots we see. But next, I'm just going to run now NSClean, but with the default pipeline mask that it creates. So if you're not supplying the mask to this NSClean step, the pipeline is going to generate a mask based on default parameters. And this mask is essentially just an array of true and false values, where true is going to indicate that the pixel is dark and false indicates that the pixel is illuminated. And so by default, the pipeline is already marking the following areas on the detector as illuminated. So they're marking pixels from any open slits, traces from failed open shutters, 5 sigma outliers, and any pixel also set to NaN is going to be set as illuminated, and that's because NaNs can kind of mess up the process of getting a background fit. And this sigma parameter is, you can modify it, and we'll do that in the next section. But for now, we're just going to use the default to see what gets returned. Same thing here. I'll just note that in this, when you're calling the NSClean step, make sure that you are not skipping it. And you also want to save the mask and the results so that we can actually look at it and evaluate before moving on to anything else. And okay, this is an important note here, though, that this step may fail to fit the background noise. And this can occur if, say, the masking is too excessive and there's not enough dark data. Because this is a procedure that considers it column by column, so one at a time. So if it does crash, you just want to kind of go in and make sure that you have some dark data in each column so that the fitting doesn't fail. And so here are plots that are going to show the mask, and in the next few plots, I'm going to show the results. And you'll see this after each process. It'll be like the same kind of plots, but different results. So here we can see the original data. You can clearly see that the 1/f noise is more prominent in the NRS2 detector. This next column is looking at just the masks, so it's just the true and false array. You can see that it's these boxy regions, and these are the bounding boxes determined from the WCS. And this is just overlaying the mask on top of the data. It's not doing any of the correction yet. But you can already see that it's not capturing all the illuminated areas on the detector. I'll explain a little bit more in the next section about this, and this is one reason why the alternate masking method that we're going to look at might be more beneficial. So if we're looking at comparing the results, we can see this is the original data, this is the clean data. Visually, we can see that the 1/f noise has been improved here, but I will note that the cleaning process can introduce some artifacts, and so it's very important that when you're using NSClean that you test out these different masking methods and really evaluate whether or not it has improved the data, or if it has introduced some unwanted artifacts that you may not want. That's important to note. And one of these effects is, this is a difference image between the two. You can see these, like, just these outliers, and that is an artifact. The large relative differences are an artifact from the cleaning process. Okay. This is also the same thing just for the NRS2 detector, but what really we want to look at probably is some of these individual 1D extracted spectra. I'm going to go ahead and skip over that for now. So yeah, so I'm only plotting two slits, one on NRS1, slit 80, and slit 11 that falls on NRS2. If we're looking at slit 80, we can see that the cleaning process does slightly change the continuum level, so that might be something to consider, but I think this is the best example of slit 11 of how the data can be improved with NSClean. As you can see here, what was negative before is now been corrected for, and it's now no longer negative. However, with this default mask, it does introduce a very specific problem between 4.5 and 5 microns for this slit, and is that we're introducing this like high frequency noise. It's causing this really negative dip compared to the original data. And this is caused by the excessive masking from the default mask. So how can we handle this is looking at alternate masking methods. And I mentioned a little bit, but some of the reasons we would actually want to maybe use the alternate masking using like a sigma based clipping instead. One example is that for M gratings, 0 order spectra may appear on the detector and they're not easily located, so those might not be masked with the default mask. As well as for the long pass filters, there might be some light that gets past the red cutoff, which is kind of what I was trying to show in the plot above, that is not in the slitted bounding box, so it doesn't get necessarily masked. Okay, so here we're doing the same thing. We're making sure two parameters though. We're gonna set the n sigma parameter to 1 to detect anything over 1 sigma of the background, and this should get more background data or dark areas on the detector between your spectra. And we also want to set this mask spectral regions to false, otherwise it'll try to use the WCS again to define the mask, which is that really boxy mask that we've seen. But with the alternate, when we're just doing a sigma-based mask, you can clearly see that we have more dark data in between these spectra, and so that'll hopefully improve the background fit that we get with NSClean. Again, these are the original data versus the clean data. Hard to tell differences from this view. You see the similar things as before, but if we look at the extracted spectra, notably slit 11, again, we're seeing that the negative flux is corrected for, but now we no longer see that negative dip we introduced with the default masking between 4.5 and 5. So the alternate masking definitely did a better job in this case. And so those are the kinds of things that you're going to want to look into when you use NSClean. You're going to want to compare different kinds of masks just to kind of see the effect it has on your data. And lastly, I'm just going to show a very simple example for one way how you can just hand modify the mask. And so in this case, there was a few snowballs I noticed in the data. So what I did is just I located them and gave it the area that I wanted to set to false in the mask to mark it as illuminated. And if we look at the mask, it's kind of like this is my contribution here. Now, I will note that since this is just an easy example I put on there, it's not necessarily going to be any better or worse than the other two versions, especially since I'm marking snowballs that not necessarily are falling on a spectra, but this is just an example of how you can do the alternate masking. I mean, the user supplied mask. So you'll want to supply this user mask parameter here, define your mask, run the pipeline, and then again, you'll see your final results. And if we look at the 1D spectra, we see some differences. So this is definitely, I think, let me go to the conclusion slide because they just plot them all next to each other. So these are all the different methods. You can clearly see that, we're doing better with the 1/f noise, but I think the bottom line is that you should definitely just confirm and make sure that you're not introducing anything worse for your spectra, more noise in your final spectra.